Let's have a look at another use of radians. We can use radians to approximate the values of sine and cos when theta, our angle, is very, very small. And remember, this only works in radians. So we've got the arc of a circle here. We're going to take radius 1. No particular reason, just makes the algebra a little bit easier. You could put the radius as r, but you're going to get factors of r cancelling out throughout your calculations. I'm then going to create a little right angle triangle here. Labelling my right angle triangle, this vertical here will be sine theta, and this horizontal along there up to this point will be cos theta, because I've got that hypotenuse of 1. What we notice is, for very small angles of theta, the difference between this curved arc and this vertical opposite is negligible. The smaller the angle theta becomes, the closer that vertical line will get to the length of this curved line there. The length of that curved line will just be 1 times theta, so that curved arc there has a length of theta. We can see, looking at this, that for very small angles measured in radians, sine theta is approximately the same as theta. Okay, that's going to be a slight overestimate of sine theta, but it's very, very close. Okay, what about cos theta? How could we figure out roughly what cos theta is? Well, we can see that cos theta goes all the way along here up to that point. So we know it's going to be very, very close to 1, but we would like to take that little adjustment into account if we can. So we're going to consider this here. Imagine that we have a right angle triangle positioned in that bit there. If I draw that out, slightly zoomed in, that is a curved section, but if theta is very, very small, we've exaggerated it here so that we can see it, we could approximate that as a straight line, and it would be very, very close to true. So that length there is sine theta. This length along the bottom is 1 minus cos theta. And that arc length there is very well approximated by theta. So we can use Pythagoras' theorem and say that theta squared is approximately the same as sine squared theta plus 1 minus cos theta all squared, which tells us that theta squared is approximately the same as sine squared theta plus 1 minus 2 cos theta plus 1. And now looking at this, we can see that we actually get theta squared. I'm just going to add that 2 cos theta over to this side. Approximately the same as, plus 1. That's where I was. Expand that bracket, we've got 1 minus 2 cos theta plus cos squared theta. You'll see in a second why I accidentally wrote 1. I was getting ahead of myself. We're going to have 1 plus cos squared theta plus sine squared theta. That is 1. Cos squared theta plus sine squared theta is 1. So that must equal 2. Excellent. We now want to make cos theta the subject of this, because remember we've already got our approximation to sine theta. We wanted an approximation to cos theta. So we can see that cos theta is approximately equal to 2 minus theta squared all over 2. We've got our very good approximation of cos theta. Cos theta is approximately the same as 1 minus theta squared over 2, and sine theta is approximately the same as theta. Okay, if you do further maths, you'll look at other ways on how to get more terms of these approximations to make them even better, but that's the idea for now. we'll just look at one example of how that can be used. Let's say that we had approximate the value of cos 3 theta over sine 2 theta. Let's just put a -1 in there so it simplifies a bit more. Using my small angle approximations, I know that cos 3 theta can be approximated by 1 minus 3 theta squared. So remember, it must be whatever the angle is, that's what we're approximating. 3 theta squared over 2 minus 1 all over, and then sine theta can be approximated by whatever this angle is there. Tidying up, my 1's cancel. That 2 and that 2 are both denominators, so that can become a 4 theta. Should make that approximately. End up with 9 theta over 4. So if I wanted to know the value of 3 cos theta minus 1 over sine 2 theta, and I knew that my angle was very, very small, I can use my small angle approximations and know that that will be roughly the same as the value of 9 theta over 4, only if theta is small and only if measured in radians.